In this video, we're going to start to talk about how to solve some force problems. And one really crucial tool that we'll use not only in this class, but in 152 to sort of understand a force and motion problem is what's called a free body diagram. So we're going to learn how to make a free body diagram. So we look back at Newton's second law here, the sum of forces. The net external force is equal to mass times acceleration. Notice the arrows, right? This is a vector equation. What that means is that the acceleration is also in the direction of the force vector. Okay, so m doesn't have a vector. This is just a scalar, but you can multiply a scalar by a vector and you're going to get a different magnitude. The acceleration magnitude isn't going to be the same as force, but it's going to be in the same direction because this scalar won't change the direction of that vector. So a net force is the sum of forces acting on an object in a certain direction. So we often resolve the second law, just like we resolve the components of any vector, into the sum of the force vectors in the x direction is equal to the acceleration in the x direction. And the sum of the forces in the y direction is equal to the acceleration in the y direction. This is really useful, right? Again, we've made these two independent equations, just like we did with projectile motion. And that means I can solve this one without having to solve this one and vice versa. Although sometimes we may want to solve them both or solve them together. They can be dealt with separately from each other. They're independent. So in this example up here, this skater here has one skater pushing her rudely on the shoulder in what we'll call the x direction and another one pushing her in the y direction. So what is the net force? Well, it's the force of one summed with the force of two, okay? And that gives you your net external force. So if there was no friction on her skates, then she would slide in this direction up here. So her acceleration would be in the same direction as the force. We simplify a sketch like this into what's called a free body diagram, in which we take the object that we're interested in, this skater here, and we turn her into a dot. And then we draw all of the forces coming out of that dot in their different directions, and that gives us a good sense of what our answer is going to be, right? We know it's going to be a sum of these two, so we figure it's going to be in this direction, right? So we'll do a little bit of practice drawing those free body diagrams. And the first one we'll start with is a mule problem, all right? So mules are, they don't like to be pulled. They are stubborn as mules. And so in this problem, Jack pulls ahead of the donkey with a force of 61 newtons. Jill pulls in a direction 45 degrees to the left at 67.9 newtons. And Jane pulls in 45 degrees to the right with 187 newtons. We want to find the magnitude and the angle of the net force on the donkey. So to draw a free body diagram, we go through this process that we'll do basically each time. You draw a sketch of the objects, and that may mean, just sort of, you don't have to draw the donkey, but, get a sense of what's happening physically. If you have a complex physical situation, see if you can draw a little sketch of it. Then we want to simplify that as a free body diagram. So we're going to start off with a dot. This step's very easy. Create a dot on your page. And then the next step is to draw arrows representing all the forces on the object. And this is the tricky one, right? We have to really think about what forces they are and in which direction they're being applied. We've talked about weight force and applied force. We'll talk about normal force in just a couple slides. And then next time we'll talk about a whole range of different forces like tension, friction, and drag. So we've drawn those arrows around our dot. Then we want to choose a coordinate system. And you might say, well, why didn't we just choose a coordinate system up here instead of just drawing that dot? And the answer is that you can actually change that coordinate system to match with your forces. You want to have as many forces in the x and y direction as you possibly can. And so you need to know what the forces are before you set up that coordinate system. And we'll see an example of that in, again, just a couple slides here. And then finally, any force that's not in the xy direction, we want to resolve the force vector into those two directions. So we want to have everything in terms of x and y directions. You can see why this is helpful, right? If I get all my forces in the xy direction, I get to skip this step, and I don't need to deal with those nasty cosines and sines. So let's draw our free body diagram here, and I've already drawn it. So we drew our dot here. And then we have to look at our forces, right? So we had one jack pulling directly in front of the donkey. So our donkey is facing in the positive x direction. There was one force pulling to the right, and then strong Jane was pulling, rather to the left, and Jane was pulling to the right with 187 newtons. So we look at this and we sort of say, what's our net force going to be? Well, clearly this vector is bigger than this one. And so there's going to be more of a pull down here. So we would expect, one, that the vector would be longer than 61, right? You know, at least you would think, 100 or so, because most of this force is being pulled in the rightward direction. So these are going to mostly sum in the x coordinate. And then we would expect it also to be down here in the fourth quadrant because this one is so much stronger than that. So I'm going to guess, I don't know, maybe 200 down here, 20 degrees or so to the right of the positive x-axis. So that'll be our guess here. To do that and find out our answer, we need to resolve and sum our vectors. So we'll start with the x direction. So we want the net external force in the x direction. So we want to sum our forces in the x direction. And to do that, we need to choose an axis, and we'll stick with this x-axis. So because we know this angle is 45, this angle is negative 45. Okay, it's important to recognize that difference because these two are not pointed in the same direction, right? So we want them to balance each other, at least in the y direction. So then we want to think about, okay, if my angles are here and here, and I want to figure out that component in the x direction, that's going to be the adjacent side of the triangle, right? If this is my triangle here, I want this side for the x direction, right? So that's going to be your adjacent. So that's cosine adjacent over hypotenuse, okay? This one too is negative 45, but I still want the adjacent here. And then if we think about this shrinking down all the way to 0, it's the same situation. It's just that this is a 0 degrees, and so cosine is going to give us that full vector. So cosine of 0 times the force of Jack, cosine of 45 times the force of Jill, and cosine of negative 45 times the force of Jane. Now cosine of negative 45 and cosine of 45 happen to be the same in this situation because they're both pulling in the rightward direction. But it's important that we remember that that's negative 45 degrees because it does matter when we use sine. So we put in our numbers here. These are given by the problem, and these are just our cosine values. And we find that our net force in the x direction is 242 newtons. Okay, not unexpected, right? Because we knew we'd have at least 60 here, plus at least 100-ish here, plus another 60 there. So that makes good sense. Now the y direction, this one is going to be pulling down and this one is going to be pulling up. So they're not going to all just sum. So we're going to be looking for a negative number somewhere. But we do the same thing. We're going to do sine because now we're looking for opposite part. Our angles are over here. So our opposite side is over here and over here. Jack is not moving at all in the y direction. So we would expect that this vector would have no y component. So let's double check when we look at our values here. So we remembered that Jane was at negative 45 degrees. Jack disappears, just like we were hoping. And Jill and Jane have opposite directions, which makes sense with our physical intuition. So this term is going to be negative. This one's going to be positive. This one's going to be bigger, right? So we would expect an overall negative number, and that's what we get. Okay, so our net force in the y direction is down at 121 newtons. Now notice this is smaller than in the x direction because we weren't just summing numbers, we were taking the difference, and they balance each other. So rather than just all adding up as they do in the x direction, they balance and cancel out in the y direction. So this is one way of stating our full vector, but the problem asks for our magnitude and direction. And this is the same process we used in 2D kinematics, right? We want to use the Pythagorean theorem to find our magnitude, and then we'll use the inverse tangent to find our theta. So here's our Pythagorean theorem. Taking our two components here, squaring them and summing them. Take the square root of that, and we get a magnitude of 271 newtons. That fits with our expectation looking at the Pythagorean theorem, right? The number's always going to be bigger than the bigger of the two numbers, but if there's much difference, it's not going to be a lot bigger, right? This term is just going to dominate this equation. So it goes up a little bit, but not a ton. In finding direction, we need to make sure we pay attention to our signs. So we do theta inverse tan of Vy over Vx. And again, that's because it's TOA, right? Opposite over adjacent. Opposite over adjacent. That means that our angle is going to be the same angle in here with reference to the positive x axis. And we find that it's negative 27. Okay, so we included that negative in the Vy term. And that makes sense because remember we thought it would be in the fourth quadrant. And it's about, we thought maybe 200 something, about 20 degrees below that x-axis, and that's pretty close to what we got. All right, so that's a straightforward just